Right, so we are going to start talking about ideal gases and the generalized compressibility chart. So we can evaluate properties of pure substances, pure meaning that there's only one type of molecule in our system that we're looking at, or working fluid. So we can evaluate properties of pure substances in the gas or the superheated region in two ways. Number one, we can look at our superheated tables if we have them. So our tables for that substance if it's in a gas phase. But we can also use an equation of state. So any equation that relates properties of a substance at an equilibrium state, such as pressure, temperature, specific volume, this is an equation of state. And one of the most simple ones that you've probably already had some exposure to is your ideal gas law. So this is your ideal gas law, and let's look at each of those little things. So M is mass, R is your specific gas constant, temperature, let's go back here actually, T is temperature, P is pressure, V is volume, and you can also divide through by mass and get things in terms of specific volume if you like. That specific gas constant is specific to whatever gas that you're talking about. And its units are kilojoules per kilogram K or BTU per pound mass degree Rankine. It is calculated based upon the universal gas constant and that gas's molar mass. So notice that that is an uppercase M, that is molar mass. You can look that up in table A1 and it's going to be in kilojoules per kilomole or pound mass per pound mole. Those are located in table A1 and A1E, and you have that available to you in your thermodynamics packet. So unfortunately, these specific gas constants they're not tabulated in your thermodynamics table packet, but it's easy enough to calculate based upon your universal gas constant and your molar mass. So your universal gas constant is, well, it's on your conversion factor sheet. It's at the very bottom, but it's 8.314 kilojoules per kilomole K, 1.986 BTU per pound mole degree Rankine, and then there's another one, 1545 foot-pound force per pound mole degree Rankine. But all of three of those are, oh, it's right there in front of me. All three of those are actually on your conversion factor sheet, and it's at the very bottom. So you'll have that accessible to you. And actually, I'm noticing, there we go, I fixed it. The foot was missing down here, this foot-pound force that was missing. But anyway, so the universal gas constant will be available to you on your equation sheet. So there's your ideal gas law. You have it available to you on your equation sheet. You just have to pay attention to your units. Be careful about that. So perfect. Hope we can use it. And honestly, probably most of the time you can. Things like air, 99% of the time you're going to be able to assume it's an ideal gas. But you do need to be cognizant of the fact that not all gases exist as ideal gases or should be modeled as ideal gases. And so we have a few rules that we can use. So one of the things that I see people messing up on is treating water as an ideal gas, and it can be treated as an ideal gas. So you could see here's a table. This is an older table out of older version of your textbook. But you could see this is a TV diagram. Here's our vapor dome, and you can see it's really only out here. I mean, all of this is superheated. All of this is water behaving as a gas, but it's really only out here that we want to treat that water as an ideal gas. So how do we need to have like a rule to figure out when can we assume that something behaves as an ideal gas. So we could see from this guy that, well, if it's at a high temperature, relative to that critical temperature, we could probably assume that it's an ideal gas. At low pressures, we can probably also assume that it's an ideal gas. And what we can do is we could define Z, which is called the compressibility factor. And this is a parameter that will allow you to define quantitatively how far away from ideal gas behavior that you are. So if it's close to 1, then it's assumed to be an ideal gas, right? If Z is equal to 1, it's an ideal gas. And the farther away that it gets, the further away from ideal gas behavior that you are. So let's look at Z for various gases as a function of temperature, the critical temperature, and the critical pressure. So this right here, oh, perfect. So you could see, yep, there we go. So you could see this is what's called our reduced temperature, and you could see the reduced pressure down here. And so you could see at various combinations of the reduced temperature and reduced pressure, you are closer to that Z value being equal to 1 than not. So this, let's see, let's go to the next guy. Okay, so the reduced temperature is calculated, it's the temperature over the critical temperature. And remember, we can look up that critical temperature. We can look that up in table A1 or A1E. And then the reduced pressure is the pressure divided by the critical pressure. Remember the critical pressure, you can look that up also in table A1 and A1E. These are unitless parameters, so you just need to make sure that your pressures are the same on the top and the bottom so that it becomes unitless. And the temperatures that you want to plug in right here have to be an absolute temperature unit. So either Kelvin or degrees Rankine is what you want to do. All right, perfect. So this is the generalized compressibility chart that you have available to you. And let's look at a few things. Okay, so what you've done, actually, let's go back and look at this guy. So what we've done is we're taking just a small portion, this box right here, and that's what we're looking at. Okay, perfect. So this is that small portion right here. So what we're going to do is we're going to notice some trends. High TR values, high reduced temperatures. Remember, the reduced temperature is T over T critical. And very low reduced pressures, which is P over the critical pressure, you're going to tend to be close to that Z value being equal to 1. So in this class, if you got a reduced temperature over 2, if you have a reduced pressure that's less than 1, or you're just close to that Z value being around about 1, so we'll do a cutoff of 0.9, then we'll say we have an ideal gas. Most of the time, 99.9% of the time, if you've got something like air or nitrogen or something that you kind of think of as a gas anyway, it's probably going to behave as a gas. But if there's ever any doubt, you should check, right? In practice, you should check to make sure that the thing that you're treating as an ideal gas, make sure it behaves as an ideal gas during the whole process that you're looking at. So just one of these things has to be true for you to assume that you have an ideal gas in this class. So let's do a real quick check here, make sure that we understand. So the question is, can we treat air as an ideal gas at 25 degrees Celsius and 1 bar? Okay. So first thing I'm going to do, I'm going to calculate my reduced temperature. So it's T over T critical. Oh, there's my T critical in table A1. My temperature is 25 degrees Celsius. Need to put at that in absolute temperature units. You notice that the critical temperature in table A1 is already there. So it's just a little reminder to you to make sure. And I see, oh, it's greater than 2 right away. So I actually don't have to do anything else. I've checked one of those boxes, so I'm good to go. I can treat it as an ideal gas. Let's do one more. So can we treat water as an ideal gas at 400 degrees Celsius and 33 bar? So higher pressure there. Let's see. So I'm going to check the critical temperature, or check the reduced pressure. Check the reduced pressure, or reduced temperature. So T over T critical. All right, well, there's my critical temperature. So if I plug things in, I see up 1.04. Okay, well, it's not, the reduced temperature is not greater than 2, so I can't automatically assume that I've got an ideal gas, but I haven't checked everything yet. I still need to check that reduced pressure, so let's check that guy. So my reduced pressure is P over P critical. My critical pressure is 220.9 bar. And if I plug in 33 bar on the top, I get 0.15. Nope, that doesn't work either. So I got one more thing to check. Now I got to pull out the compressibility chart, but that's okay. So I'm going to pull that guy out. So I find my line corresponding to, I mean, it's not exactly, but it's pretty close, right? My reduced temperature of about 1, and I'm going to trace it on over here to see where it crosses over with a reduced pressure of 0.15. And I can see, oh, look at that. Z is greater than 0.9. So even though I didn't check the box for the other two, I do check the box for Z being greater than 0.9, basically pretty close to 1. So all right, so let's do a problem here. So the question is, what's the specific volume of air at 25 degrees Celsius and 1 bar? So let's write down what I've got and what I'm going to assume. I'm going to see, can I use my ideal gas law? Most of the time I'm going to tell you can, especially if it's air or nitrogen or CO2, something like that. But we'll do due diligence, right? So we'll check it out. So my critical temperature for air, I can look that guy up. It's 133. Plug things in. I see that my reduced temperature is greater than 2. So I'm good to go. I can assume that I've got an ideal gas. Now the thing I need to do is apply my ideal gas law. So I'm looking for specific volume. Perfect. Remember that R is my specific gas constant. I need to calculate that based upon my universal gas constant and the molar mass for air. And so I'm going to plug those things in. I would go through the process of like actually writing down those units and seeing how things cancel out. So here's my specific gas constant calculation, here's my temperature, and here's my pressure. But I need to do some unit conversions here to make sure that everything boils down to meters cubed per kilogram here. So there you go. So make sure, I guess with the ideal gas law stuff, especially if you're in English units, make sure that you write down those and if you're in SI units as well, but make sure you write down your units to make sure that you don't mess anything up, okay? All right, well, thank you very much for watching, and let me know if you have any questions.